So I'm going to discuss how we can use the techniques of numerical differentiation and integration in a simple Schrödinger equation solver. So we're going to consider simply a particle in a well. I've put in a little bit of explanatory text here and I'll make the notebook available. And what we're going to do is we're going to find the ground state energy function by minimizing the energy. So we're going to be using the optimization techniques of conjugate gradients. We're also going to use finite differences to do the second derivative, so the kinetic energy, and we're going to use numerical integration to evaluate various quantities. So let's start with some physical parameters. And we're going to be assuming that we're working in atomic units. So that means that distance is in Bohr, distances in Bohr radii. One Bohr radius is about half an angstrom, 0.529 angstroms. 1 angstrom is 10 to the minus 9 meters. And energies are in Hartrees. A Hartree is 27.2116 electron volts. And of course, 1 electron volt is 1.6 by 10 to the minus 19 joules. So you can convert if you want. I'm going to make it a box which is going to have a length of 5 Bohr radii, and I'm going to set a distance spacing of 0.01. There's a subtlety here that I haven't fully explored, which is that if you make this too small, so below about 10 to the minus 3, then you get some physical instabilities. I want to understand that, and I will confirm exactly what's going on when I have understood that properly. We now want to create a number of points, so n is going to be an integer of L divided by dx, and then of course we have to add 1 because we want beginning and end, and we'll create an array of x values, which is numpy.linspace of 0, 0, L, n. And let's create some space for our wave function. Wave function psi is equal to numpy.zeros of n. Okay, so now we need some functions. Let's start by writing a second derivative function, and we're going to want to pass it the wave function psi and the spacing dx. So we're going to say finite difference second derivative, and we'll say that the inputs, of course, are psi, wave function, and dx is the grid spacing, and the output is simply d2 psi by, which is the second derivative. And so we will create psi p, that's a positive, a shifted 1, so np dot roll of psi comma minus 1. Remember that the minus 1 is applied to the indexing. And then psi m is going to be numpy dot roll of psi comma 1. Of course, with a second derivative, this doesn't actually matter because the answer is symmetric. Psi p minus 2 times psi plus psi m, and we divide that by dx times dx. So this is the second derivative. Now, there's always going to be a question about the edges. We're going to need to be quite careful about the edges. For now, what I'm going to do is I'm going to do a sort of a working assumption, which is that the second derivative at the exact boundary is simply the same as the second derivative one step in. That may not be the best approximation, but it works well enough. d2 psi of minus 2, sorry, that should be minus 1, is equal to d2 psi of minus 2. And then I'll return d2 psi. So what we've done is we've created the second derivative using finite differences. We're using numpy.roll to be efficient, and then we've decided on a specific approximation for the second derivative at the edges. We'll need to evaluate the energy, and here we'll want to have a wave function and a potential and a dx. And what we're going to be doing is actually evaluating this integral up here. So we'll say evaluate the energy. Let's put the proper spelling of evaluate in there using numerical integration. And I'm also going to note including normalization. And again, we're going to have inputs, which will be psi, which is the wave function. We're going to have v, which is the potential. And we're going to have dx, which is the grid spacing. And the output will simply be E, the energy. So psi norm is going to be integrate dot trapezoid. I'm going to use trapezoid because I don't have to worry about the number of points that I'm using, which you would get with the Simpsons rule. So I'm using the SciPy integrate module. I'm doing psi times psi because that's psi squared. I'm passing it the set of x positions, x val, and then I will use that to normalize the result. Then I need to think about the Hamiltonian acting on the wave function h psi, and that's going to be minus 0.5 times the second derivative of psi comma dx. So that's the kinetic energy. I'm going to add on v times psi. And then the energy is going to equal, we're going to need to integrate dot trapezoid. We're going to do psi times h psi comma x val. That's the top of this little expression here. That's the integral, and we'll need to divide by the bottom. That's psi norm. And we'll return the energy. It's as simple as that. Okay, so let's define the potential. So potential is going to be numpy.zeros of n. That'll give us a square well. I know that the analytic wave function psi analytic is going to be some kind of normalization constant, which I'm not worrying about for now, but it's basically a sine. So it's numpy.sine of numpy.pi times the x values divided by L. And so I'm going to write out, so the numerical ground state energy is, and then we're going to say eval energy of psi comma v, pot comma dx. And then I'm going to close the quotes there. That's a formatted print statement. And then, of course, we need to compare that to something. So we're going to say formatted print statement of the analytic ground state energy is, and I'll put in an extra space to make it pretty, and it's a half pi squared divided by L squared. That's a standard result. You can work that out for yourself. Oh dear, what have I done wrong here? Okay, so I've got a nan. That's going to be in the return from the energy divided by psi norm. That should be correct. Have I set up? So, oh, I've sent it psi, not psi analytic. Psi was, of course, set to 0 up here. So, of course, I'm getting 0. Rerun it, and there we go. So we see that the numerical ground state energy is different to the analytic. It's about 1 microhartree different, and that's all going to come from the approximations of the numerical integration and differentiation we've made. At this stage, this is not variational. In other words, it doesn't matter that the energy is slightly lower than the analytic ground state because we know what the analytic wave function is. We've used the analytic wave function. So that difference is just an expression of how bad our integration is. And a microhartree is actually pretty good. Let's now create a gradient function. So we want a gradient function here. I didn't need to put that comment in there, but I'm just making a note to myself. So now what I'm wanting to do is to create the gradient dE by d psi, because then I can pass that to the conjugate gradient routine. And again, I'm going to need v and psi and dx. I'm not going to go through how I derived this gradient. That's maybe third-year quantum mechanics and involves understanding how basis set works. Just for now, accept that this is the correct gradient. The energy with respect to wave function. And I'm going to say inputs will be psi, which is the wave function. I'm going to say v, which is the potential on the grid. And dx is the grid spacing. And then the output is just dE d psi, which is the gradient. Again, we're going to need to normalize. Integrate dot trapezoid, and we're going to give it psi times psi and x val. I'm going to say that the energy, we need the energy here, is eval energy of psi v dx, and then the gradient, grad psi, is given by 2 times, and then we have minus a half times the second derivative of psi comma dx plus v times psi minus e times psi, and we divide that by psi norm. I can show you how to do that if you're interested, but it's not relevant to this. And now we're going to fix the edges to be 0. Again, maybe not strictly necessary, but it does seem to help with the stability of this method. I know that technically for the exact solution, this shouldn't in fact be non-zero, but it's given that we're going to be adding the gradient onto the wave function and we need the wave function itself to be 0 at the ends, this is necessary for total stability. It's one of those mixes between numerical stability and the constraints we're applying. Okay, there's our gradient function. What are we going to do for our initial wave function? Well, let's start with a Gaussian. So we're going to say that psi from 1 to -1. So I'm going to keep the edges 0. It's going to be numpy.exp of minus 5.0 times x val from 1 to -1. Make sure that those match the limits on both the left and right hand sides. Minus L over 2. So that's putting the origin at the middle, and I'm going to square that. So it's just a simple Gaussian. I'm going to make the potential numpy.zeros. I probably define that above, but we're going to keep it there for now. And let's just plot that initial x val comma psi. Just check that works. Yes, that's sensible. Okay, so I can do plt dot x label should be x in Bohr. Plt dot y label can be. Actually, let's make this a. I need r there, and then I want psi. And I can put a title of initial wave function. There we go. That's our initial graph. So now we're going to pass this to the SciPy optimize routine. So I want to store the answer. So that's going to be some kind of thing called ret for return. And I want optimize.minimize. I want the function eval energy. I'm going to give it psi as my input. The arguments that I pass to eval energy, apart from psi, are pot and dx. The method we're using is the conjugate gradient method. The Jacobian, so that's the derivative, is given by dE d psi, and I'm going to specify a tolerance 1e minus 4. The tolerance here essentially just looks at the RMS magnitude of the gradient, so it stops it from going on for too long. I'm just going to copy some existing code that I have just to save time, where I'm just going to look at the output for the here. So I'm going to print out the success of the method. I'm going to look at what the total energy was, how many iterations there were, the final message, and then I'm going to compare the energy we've evaluated against the numerical and the analytic versions of the exact problem. So let's run that. Okay, that took 1,500 iterations. That's maybe a few more than you would want. It stopped with an energy which is very, very close to the numerical energy of the exact solution. And again, we're just slightly below the analytic energy, but notice that our optimized energy is above the numerical version of the exact energy. And that's reassuring because this is a variational problem. Let's plot out the wave function, both the wave function and the analytic one. Again, I'm just going to use existing code because this is all fairly trivial. So I'm going to produce the normalization for the analytic solution and the normalization for the numerical solution. I'm going to plot both of those and put some labels on. And lo and behold, they're right on top of each other. If I plot the difference between them, that's actually more interesting because we can actually then see where the errors are and how big the errors are. So again, I'm plotting the difference and I'm just taking the difference between the two. And we see, okay, we can't quite see that, so let's comment out the title just for a moment. 10 to the minus 6, so that's extremely close. And just finally, let's plot the gradient, the search direction, and also just check the RMS magnitude. So the way we're going to do that is, okay, so here's the plot of dE psi, here are some labels, and then this final line here prints, we take the dot product of the search direction with itself, we then divide by the number of points, and we take the square root. So the RMS direction magnitude is 3 by 10 to the minus 5. Here we see a plot of the search direction, which is down at 10 to the minus 5, so you can see why we've converged. So this is a very simple system, of course, but actually the overall approach that we've taken here is very, very similar to the approach which is used in big commercial research codes for solving the Schrödinger equation, the electronic structure of solids. The second derivative on a grid, that is sometimes used. It's difficult to get that as accurate. The integration of energy is used all the time. And this kind of gradient being fed into a conjugate gradient solver is the basis of all of my research, and we use it to find the ground state. So you can see here why we use optimizers. During the optimization, you have to find the root of, or the minimum of a function, which of course is the root of the gradient. So we've covered the root finding, we've covered optimization, we've covered numerical integration and numerical differentiation. So these are all techniques which are extremely important and useful.